So looking at our list here, everybody should have submitted their exercise 6 from last week. So you'll have, it should be in by now. It's supposed to be in at the start of class, but I'll accept it up to the end of today's class. So next thing we're going to look at is review of exercise 5. Mink, I see you there. So exercise 5 was the infiltration tank, a little estimate. So I've got a little sketch here. So you were given this information in the question. So you're told that the tank is 5.9 meters wide, and it was 9.1 meters long, and it was 0.9 meters tall. Nima, you have a question? If I've asked you questions on your either your marked assignment or your marked, I guess, midterm, if you can send me an email with the question that I asked you and then your response, that would be appreciated. Okay, so back to week 5. So we were given this tank with those dimensions. We were also told what the finished grade is here. So that was 51.72 meters. We were told that we needed 150 millimeters of gravel underneath the tank. And we wanted to be at least 150 millimeters wider than the tank all the way around for our bottom excavation. So that's where these numbers come in. So this 9.4 is simply the length of the tank plus 150 on either end. Similar with the width here. So it's the given tank width plus 150 on either end, gives you 6.2. So what else have I written here? So we're told what the invert of the tank is. So this 50.21 meters. You needed to deduct your 150 millimeters of gravel. So you needed to be lower by 150 millimeters. So that means your bottom of excavation was at elevation 50.06. So the difference between that bottom excavation and your finished grade up here is your excavation depth, which is 1.66. So then you're simply calculating volumes in here. So I looked at an X direction and then a Y direction. So that's what these two sections are. So let's go into, I've got an Excel spreadsheet here that we can go through the assignment. Yes, Nima, you had a question?
No, the same question I asked. Thank you.
Okay. Karen Beer, do you have a question? No? Okay, I'm going to mute your microphone, Karen Beer. Okay, thank you. Okay, so on the assignment, the wording in the assignment, I was a little bit tricky with it. I mentioned the quality of the excavated material was, I forget the exact wording, but the intention was that the type of excavation that you were in, the ground was pretty good. So you, according to WCB, you could be steeper than 1-to-1. According to the PowerPoint presentation that we looked at during week 5, you could be as steep as 3/4 to 1, which is steeper than 1-to-1. So with my solution here, I've done a solution based on cut slopes of 0.75 to 1, and then most of you selected a 1-to-1 excavation slope, which I didn't mark you wrong on, but you can see that the volumes are quite a bit bigger with a 1-to-1 versus 3/4 to 1, which translates into more dollars. So your estimate based on a 1-to-1 slope would be more dollars compared to an estimate that was based on 3/4 to 1. So as we go through here, if the answer is different based on 3/4 to 1 or 1-to-1, I'll mention the differences as we go through. So looking at the excavation to grade, so we've calculated that the cut depth was 1.66 meters to the bottom of the 150 millimeters of gravel. So what this solution shows is a plan area on the bottom of the excavation, which is this line, and then a plan area at the top of the excavation, which is the next line down here. And then basically I add the two together, divide by 2, which shows up in this line, and then multiply by the depth, and that gives you your excavation volume. So the calculation is basically the same, whether you're using 3/4 to 1 or 1-to-1. The only difference is, if I zoom in here, when you're doing your top excavation, so hopefully everyone understands the bottom. So the given 5.9 width plus your 150 on either end. So that gives you your overall width of excavation. And then same thing with the length. So you're given the 9.1, and then you add 150 on either end. Multiply those two together, gives you this area on the bottom of the excavation. So at the top, you start with the same number. So this 6.2 is simply the width, the 5.9 width, plus 150 plus 150. So I've skipped the step of adding those. I've just shown the 6.2 here. So with the 3/4 to 1 slope, you start with the 6.2, and then so you're adding across the top. If I jump back to my sketch here just for a second. So with that first one that we're looking at, the 6.2, so we're looking in the Y direction. So if I come up here and here, that's the 6.2. So then we're adding this width here and that width there. So depending on what slope angle we use, right, that distance will be either longer with a 1-to-1 slope. So maybe a 1-to-1 is something like this, and it's a little steeper with a 3/4 to 1. So it makes this distance smaller. So if I jump back to the Excel spreadsheet, so that's 6.2, so that's the width of the tank plus the 300 of gravels. So then we add 1.66 times 3/4. So that 3/4, so times 3 divided by 4 is what that is. That accounts for your 3/4 to 1 slope. And then times 2 because there's 2 of those. So if we were doing a 1-to-1 slope here, you would not have this 3/4 in your calculation. You would simply do 6.2 plus 1.66 plus 1.66. That would give you your overall width at the top of the excavation. And then similarly, for the overall length at the top, you start with 9.4, you add the 1.66, do your adjustment for your slope, and times 2 because there's 2 of them. So you multiply this calculation times this calculation to give you your overall plan area at the top of the slope, which for a 3/4 to 1 is 103 square meters. So then to calculate the excavation volume, you simply add the 103 square meters at the top plus the 58 square meters at the bottom of the excavation. Divide those by 2, so that gives you your average plan area of excavation, so plan view area, and then multiply by your excavation depth. So for 3/4 to 1 cut slope, your excavation volume is 134 cubic meters. And if you did the calculation for a 1-to-1 slope, you would have 148.9. I gave some leeway there. It didn't have to be, your answer didn't have to be exactly these numbers. So if they were relatively close, I didn't take any marks off. So those are your excavation volumes. So for the estimate, so that calculates your quantity. Now you have to determine your hours. Man Moen has a question. So the depth, so this 1.66 number here, I'll go back to the sketch. So you're given the top elevation. You're given that number. My chat box is in the way here. There we go. Okay, so you're given this 51.72 elevation up here. So that's your starting ground elevation right there. You're also given the bottom of the tank elevation of 50.21. So you're told to dig out a further 0.15 meters for the bedding. So 51.72 minus 50.21. And then you add an additional 0.15 meters, and that gives you your overall excavation depth. Okay, so we have our calculated volumes here, depending on which one you used. So then your crew to excavate is your excavator, the operator for the machine, and then you would have a laborer on the ground. So your number of hours is simply whichever cut volume you calculated, divided by 30 cubic meters per hour. So this number was also given to you in the question, this 30 cubic meters per hour. So depending on which slope you used, you would, if you did 3/4 to 1, you would get 4.47 hours. If you did 1 to 1, you get 4.96. You should round those. Don't use 4.47 in your estimate. Either use 4.5 or round it up to 5. Same thing with the 1 to 1. This one you should round up to 5. You're not going to spend 4.96 hours doing something. You're either going to spend 4 hours, 4.5, or 5 hours. So I've got 5 hours here. So you were given the rates. So you would come up with a value here. The next task was, this didn't have to be in order. You can do haul off at the end of your estimate. This is just the way I've shown it here. So I've got the haul off is, again, in the question, you were told that the material, the excavated material, was acceptable for backfilling with. So it was good enough, the engineer would let you backfill the infiltration tank with the excavated material. So that means you do not have to haul all of the excavation off site, which a fair number of you did not pick up on that. So how much do we have to haul off? Well, there's two different numbers that we need to calculate first. So one is being the volume of the tank itself. So of course, we're not going to backfill the tank with excavated material. So the volume of the tank needs to be hauled off. So it's simply the three numbers that were given multiplied together. So 0.9 times 5.9 times 9.1. So there's 48 cubic meters of volume that the tank displaces. So that will be hauled off. That's this calculation here. So the other calculation is the amount of import gravel that we're purchasing. So the question tells you that there's 150 millimeters of gravel beneath the tank, beneath the infiltration tank. There's an additional 150 millimeters on top of the tank. And then there's a minimum of 150 all the way around the tank, so on the sides. So basically what you have to do is calculate the surface area of all 6 sides of the tank. So once you have that area, you multiply it by 0.15 meters, and that volume is the volume of gravel that you're going to be purchasing to be placing in the excavation. So again, that volume of material needs to be hauled off of the excavated. So I did a sample the calculation here. So the top and bottom. So I did I show 9.4 here, but again, that's the 9.1 tank length plus 150 on either end. So that's 9.4 multiplied by 6.2. So same sort of calculation. The given 5.9 width plus 150 on either side gives you 6.2. So those two multiplied together times 150 for thickness times 2 for top of tank and bottom of tank. So it gives you approximately 18 cubic meters for that volume. And then the sides. So what I show here is, so 9.1 plus 5.9. So that's the length of the tank plus the width of the tank. So times 2. So that gives you your circumference all the way around the tank. So that's the distance all the way around the tank. Multiplied by the height. So that's the surface area of all 4 vertical sides around the tank. And then again, multiplied by 0.15 meters for thickness of gravel. And that's approximately 4 cubic meters for the sides. So you add those two numbers together, that gives you a subtotal of 22 for gravels. And then as we previously calculated, you had 48 cubic meters for the tank volume itself. So those two numbers together give you 70 total. So we're saying we need to haul off 70 cubic meters. So the question tells us that our truck and pup, or truck and pups, plural, that we're using to haul off with can carry 10 cubic meters each. So 70 cubic meters of haul off at 10 cubic meters per haul unit gives us 7 loads, so that's here. So we have to haul off 7 loads. So that's the number of loads. This should not be 15. So if we have 7 loads, we have a truck and a pup, so that means a truck and a trailer. So it's 7 times 2 for number of boxes. So tipping fee is 14 boxes. So the hours for the truck and pup. So here's that calculation. So we've got 45 minutes hauling to the dump, 45 minutes back, 20 minutes to load, and then an allowance of 10 minutes at the dump site. So add all those together gives you 120 minutes. So, which is of course 2 hours. So 2 hours per load times 7 loads is 14 hours of your haul units. So again, you're given the hourly rate for the truck and pup, and you're given the cost per box for the tipping fee. Any questions so far? No? Okay. So carrying on, so my next task was placing the granular fill. So again, well, not again, but placing the granular fill can be done in one task. You don't have to show it in two. So I've got a note here. Task 3 and 6 could be lumped together. I'm showing them separately just to make it perfectly clear that I am placing all the gravel. It's important to set up your estimate so that you can understand it, so that you can follow it as you go through it. You're likely going to have to explain it to your boss or like a manager type person. So it needs to be easily followable by you and whoever you're explaining it to. So just keep that in mind. So I've broken out the two different granular backfill tasks. So the first one is the 150 millimeter depth below the tank structure. So it's the area, the surface area underneath the tank, including my 150 additional length on all four sides. So that area times 150 thick is approximately 9 cubic meters. So it's 10 cubic meters an hour is what you backfill at. So it's basically 1 hour. So I've got my crew here for an hour, and then I've purchased the required tons. So simply 9 times 2 tons per cubic. So the unit rate for my gravel was $18 per ton. So that's listed in the question. And then I've added PST, so I've multiplied by 1.07. So this is your hourly rate, or sorry, your per ton rate for the purchased gravel, including the PST tax. So 1926. So those two multiplied together gives you that. So once the base gravel is down, we go ahead and install the filter fabric. So you're told in the question that each roll is 5 meters wide by 100 meters long. So there's 500 square meters of geotextile. So it's more than enough to do this project. We still purchased an entire roll of it because maybe we can't use it elsewhere. So the whole cost of the entire roll needs to go in the estimate. You can't buy half a roll of geotextile. It's full rolls. So again, your cost per roll, so you were given $500 per roll. Again, I've multiplied by 1.07 to add the PST tax. Works out to $535 per roll. There's my hourly rates. So down to the modules. So you had to calculate your number of modules. So I believe everybody got that right. So just to make sure, in case somebody did get it incorrect. So the width of the infiltration tank was 5.9 meters wide. So each individual module is 0.457 meters. So that means you need 13 modules wide. The infiltration tank is 9.1 meters long. Each individual module for the tank is 0.9 meters long. So dividing those two means you have 10 modules long. So you're 13 wide by 10 long. And then the height of the entire tank is 0.9 meters. And each module, again, is 457 meters. So you need 2 modules tall. So you simply multiply all those together. So 13 times 10 times 2 gives you 260. So here's our install time here. So you're told in the question that each individual module takes 5 minutes. So 260 individual modules times 5 minutes each is 1,300 minutes. I'm just adjusting this here. So yes, 22 hours. So 260 modules times 5 minutes each is 1,300 total minutes. So divided by 60, of course, 60 minutes in an hour is 22 hours of work required. So you're told that each module is installed with the excavator. So you have an operator with the excavator, and then you have the extra person, all at 22 hours and their rates. Again, those are all given to you. The infiltration tank, so we had 260 modules. We're told that each module is $125 delivered to site. Plus you had to, again, add your PST tax. So multiply by 1.07 gives you $133.75 per module. So there's your total cost there. So this is the rest of your granular. So we calculated a total of 22 in a previous step. So we've already installed 9. So that is remaining is 13. So 13 cubic meters at 10 cubic meters per hour is either 1.5 or 2 hours. Again, as long as you chose one of those, I didn't mark you wrong. So this one has 2 hours in it. 13 times 2 is 26 tons. Again, your per ton rate, including your PST. Oops. So yeah, that was this one here. So then the backfilling of the native material, which is the balance of the excavated. So you've hauled some off. That is remaining, you will put back into the hole after you put the infiltration tank in with the gravels. So we've got, using the 3/4 to 1 excavation volume, we had 135 cubic meters of overall excavation. We subtracted the tank volume, and we subtract the gravel, the import gravel volume, and that leaves us with 65 cubic meters of native backfill to go back into the hole. So 65 is based on 3/4 to 1. If you use 1 to 1, your calculation should have been approximately 80 cubic meters. Doing that same calculation, so starting out with, say, 149 cubic meters, subtract 48, subtract 22, gives you about, say, 80 cubic meters of native backfill to go back in. So if you use 65 cubic meters at 10 cubic meters per hour, means you have 6.5 hours for your crew. Or if you use the 1 to 1 slopes, you would have about 8 hours of crew here. So again, you're given rates. So here's your crew, excavator operator, labor, and then your compaction equipment. So you should have had somewhere in the range of $46,000. Now this is based on the 3/4 to 1. Your 1 to 1 slopes would have been, this overall number would have been higher. Okay, any questions on that exercise 5? Okay, so that means we can jump into the PowerPoint for today's lesson. Step away. Okay, so here comes the PowerPoint. Okay, so week 7 this week, we are looking at advanced earthworks techniques. So I will, before we go into this PowerPoint, let me bring up a website that I recommend you look at some point after class. Okay, so make sure I'm on the right site here. Looks like they've changed their website since I've seen it last. They had great photos and little videos of all these different ground improvement techniques, which are no longer there. That's unfortunate. Oh, here we go. Okay, so let me share my screen here again. So the name of the site is, let me just go back here. So it's Hayward Baker. So Hayward as in dog, and then Baker, Baker. So Hayward Baker. So it's that right there, all one word, of course, .com. So this company does all of these different techniques that we're going to look at in our PowerPoint presentation. So I recommend quickly having a look at their website. It gives you little video clips on the basics of how each individual technique works, what it does, how it works. So I'm not going to get into it in great detail through our PowerPoint, but you can learn additional information on their website. Okay, so let me go back to the PowerPoint. Maybe I'll write that on the scratch pad. So I'll write it big enough. So Hayward Baker. And then look under expertise. Yes, that's it right there. Thank you, Rodney. There you go, that works. Okay, shall share my PowerPoint screen one more time. Okay, so advanced earthworks techniques. So some of the techniques that we'll touch on, some quicker than others. Again, I'm not going to go into excessive detail on each of these. We're just going to touch on most of them, just to give you, I guess, a little bit of information on different techniques that are out there. Of course, there's a whole lot more information on the web. Googling any of these techniques will give you mountains of information on it. The first one there, so deep excavations. That's typically what you see in places like downtown Vancouver, where a high rise is being built. So you've got a really deep hole in the ground, multiple stories deep, possibly for multiple levels of underground parking, as well as the large foundations for the high-rise building itself. So you can't slope the excavation. So if you think about a building footprint in downtown Vancouver, so if it's a 10-meter deep excavation, if you tried to do a 1-to-1 excavation slope, your slopes would be way out into all the surrounding roads. Actually, you would probably cut off the entire road network around that building with 1-to-1 slopes. So there's different techniques that are available that can allow you to excavate vertically for these deep excavations. We'll get into a few of those a little bit later today. So shoring and anchoring. So those are some of the techniques that we'll look at today. So shoring meaning like shotcrete shoring. So we'll do an example today of shotcrete with soil anchors. So that's a technique for doing vertical excavations where the material will not stand there on its own, so it has to be shored. So a shoring technique has to be utilized. Other methods include things like pile driving. So different types of piles. So there's round piles, so pipe piles. There's H piles. There's wood piles. So think of a wood post, almost like a telephone pole, only not quite as big in diameter. Those types of piles are used, so the steel piles can be used to increase the bearing capacity of the ground. So if the ground is too soft to build a big building on, you can pound in these steel pipe piles, and then the building foundation sits on those pipe piles. So the pipes are what supports the building, not the ground. Other methods of pile driving, for instance, the wood piles that I mentioned, those are typically used to increase the density of the ground. So if the ground again is too soft to build a structure on, you can pound in all these wood piles. So the purpose of the wood pile is to squeeze the ground into itself. So as the wood goes in, it's pushing the dirt out to the sides. So if you pound enough wood piles in, the ground eventually becomes more dense and is then able to carry heavier loads, such as a building. So that next one there, soil improvement, alternative methods. So some different methods there. So jet grouting, vibrodensification, soil mixing. All three of those are on Hayward Baker's website. So I recommend having a look at those. We're not going to get into those techniques in this course. Just be aware that they're there. Again, they're used to various purposes. Increase the density of the ground. That's probably the biggest one. Prevent water from entering an excavation. Yeah, those are probably the two biggest purposes. Again, if you increase the density of the ground, that means heavier loads can be imposed on that ground, meaning a new building could be built there, for example. So looking at that first one, so deep excavations, some elements to consider. So sloping, area available. So I mentioned that on the previous slide. So again, if you think about your deep excavation in a high density city, such as City of Vancouver, there isn't enough room to slope your excavation. You need to have vertical sides. Well, typically there's not enough room. I shouldn't say there always is not enough room. So other things to consider are the depth of the excavation. Do you have an excavator or some type of digging apparatus that can reach the bottom from the top? Or does your excavation equipment have to be in the hole? So there's some logistics there to think of. So maybe if your excavator can't quite reach the bottom, maybe you need to rent a bigger excavator to get a longer reach. So other things to consider, shoring. The size of the shoring, and do you have a room available to install the shoring? So another item there is dewatering. So if you're digging deep enough into the ground, no matter where you are, you're eventually going to hit the water table. So you have to deal with the water. You have to pump it out, you have to get rid of it so that you can build the foundation of whatever you're building. So you typically cannot install like a bedding gravel in standing water, so in puddles of water. The ground has to be dry. So if you're pumping out groundwater, do you need to treat that water? So right here, this water treatment item. These types of things would be specified in the soils report for the in the tender document that you're looking at. So it's not up to you as the estimator to guess this information. Water level would be provided to you, or it should be. Next one down there, soil conditions, permeability. So depending on the type of soil, so whether it's clay, silt, sand, till, etc., will regulate the amount of water that comes into your excavation. So that goes to the permeability part here. So the more permeable a soil is, the more water can flow through it in a given area. So with clays and silts, not very permeable, meaning not a whole lot of groundwater is going to seep through it, versus a sandy type material, water is really going to flow through sand. If you think of being at the beach and you dig a hole right on the shore, you don't have to go down very far to find the ocean water. It's usually right there, and water flows into the hole typically fairly quickly. So some other things to consider, things like equipment access. Maybe you need a big crane to install different methods of shoring. So is there room for that large crane to set up on the job site? Or do you need to, possibly close a lane down or close 2 lanes down? So those are things to consider. Personnel access. So things like if you've got this deep excavation, for example, this 10-meter deep excavation, how do you get your crew down to the bottom of the excavation to start, you know, setting forms for footings, that type of thing. You need to get people down to the bottom. So if it's that deep of a hole, typically you wouldn't use ladders. You would set up a scaffolding type stair tower. Those can be rented, fabricated on site. So personnel and equipment. So the workers carrying their hand tools, carrying, you know, bits of lumber, you know, plywood, etc., all that type of stuff. How do you get it down to the bottom? So that leads into the materials here. So the last one there, handling excavated material. So with your deep excavation, if you have an excavator on the top, so at say road surface, can that excavator reach the bottom? If it can, then likely that excavator can remove the material from the bottom. Now it's likely that that excavator, if the hole is big enough length and width-wise, that the excavator can't reach the middle. So you would more than likely have to bring in an excavator and fly it in with a crane. So pick the excavator up with a crane and lower it down into the hole. So that machine, the excavator in the hole, would dig out kind of the center portion of the hole and pass that excavated material over to the side where the excavator that's on the top can reach it and load it out into the trucks. So you may need more than one excavator to dig deep holes. You regularly do need more than one, sometimes two or three. So here's a utility installation. Looks like the ground is good enough that the slopes are steeper than 1-to-1. So they've got some bedding in here over top of the pipe. Looks like it's being wrapped with, it looks like a geotextile. So there's your crew access, so up this ladder. So that's considered a high angle slope, so a steep slope. So then you have your low angle slope, which is this slope here. So that's flatter than 1-to-1. Again, there's more geotextile on the bottom. Kind of hard to tell what they're building there. But obviously this excavated volume with this flatter slope is quite a bit higher than this excavated volume with the steeper slope. And we saw that in the review of exercise 5. The steepness of your cut slopes significantly affects the volume of excavation that you have. So that was sloping, so into shoring here. So we've seen the trench cage before, so the utility pipe is sticking out of it. So the cage is there so that the workers can go inside the cage and do their work in there safely. So if the trench walls were to fail, the trench cage would hold the dirt out so the workers wouldn't be buried. So this is anchor shoring. So this would be your shotcrete wall type system. So shotcrete meaning it's concrete, but it's blown out of a hose. So using pneumatic or air pressure. So it's shot onto the wall. And then there's where the anchoring part comes from is on a required spacing, anchors are drilled into the wall to help support the shotcrete. So we'll do an example of that later today on how to calculate those quantities. So shotcrete, anchors, groaning, all that type of system. So you can see they've got, there's a handrail system here. So there's a job site fabricated handrail, so people can walk along here so they can't fall into the excavation. Then there's this hoarding, as it's called, on the top. So on the other side of this is where the public is, so they can't see in, is what that's for. Again, it keeps the public out. It's high enough. It's quite a bit higher than the handrail. This is probably at least 1.8 meters tall, maybe 2.4 meters or 8 feet. So it's fairly tall. So other methods of shoring, this one here, this is what my company does a lot of, the work that we do. We typically build pump stations. So pump stations are normally built right close to large water bodies, so the ocean or major rivers. They're usually quite deep in the ground. So of course, if you dig that deep, you're going to hit groundwater fairly quickly. So you need to construct a shoring system where you can have vertical walls. So these are individual, so these are called sheet piles. So this Z, this kind of bent Z shape, is a single sheet. And we can only see the tip of it that's sticking out of the ground. But it would be anywhere from 12 to 15 meters long, possibly longer depending on the ground. So at the connection of the next sheet, they interlock together. So they slide down one another. So they're all tied together. So when you install them in this box shape, the box is quite sturdy. There's additional steel that's added. So these are called Wailers, these big steel beams. They help provide the sheets with additional, making them more rigid, so they're stiffer. And then even sometimes you have these cross beams to help the Wailers. So again, making the structure more stiff, more rigid, so that you can dig down inside as deep as you need to go, along with your dewatering system. So all of these type systems have a dewatering type system included with them. So well points, that type of thing. So that after you've dug the excavation out, the bottom of the hole is dry so that you can go to work in there. So here's their access. They've got a ladder, should be tied off. There's another ladder. Looks like they have 2 layers of Wailers. So this whole cofferdam system would be designed by your engineer. So the contractor has to design this. Just be aware of that. So here's our columns and anchors. So another type of shoring system. So columns have been driven in here. Again with anchors, so anchors going into the slope. So again, it's another method to have a vertical excavated face, so that you don't have to, one-to-one this, taking up increased room. Looks like this may be a dewatering method, some type of deep well system. So some other types of dewatering. Here's the typical sump pump. So the pump is just dropped into a slightly deeper hole than all the surrounding surface, all the surrounding ground. So the water finds the low spot, which is here. So the pump is in that hole. So the tire just allows the hose to come out and not get kinked. So all the water in this excavation would find its way to this low point here, and then the pump could pump it out into the settling pond or whatever they're happening to use. So this other photo here is this is your well point dewatering system. So dewatering wells. So here's their excavation. Actually, this whole thing is probably the excavation. So these pipes here go all the way around, and they likely come around this side as well. So Those are the header pipes. So coming down off of there are individual, these yellow hoses. Those connect to individual pumps. Sorry, this is a vacuum type system. So those are individual pipes that go into the ground with holes in them that allow the groundwater in. And then there's a pump up here that creates a really big vacuum, so high suction. So it's sucking on all of these header pipes, which in turn sucks on all these down pipes into the ground. So it's basically what it does is it pulls all the groundwater that's in the ground, pulls them up all these yellow pipes into the connected header pipe, and then the header is connected to the main pump, which is producing the vacuum, which is doing all the sucking, and then it discharges to again to a settling pond, to wherever they need to discharge to. Okay, so oops. Okay, so next here, so handling of excavated material. So you can see on this slide on the left, it's like it says, it's quite congested. So looks like you've got maybe shotcrete type walls here with anchors. So then these pipes here would be called struts. So those are braces in each corner of the excavation. So they're pushing on the steel Wailers. Again, those are those steel beams that are helping support the shoring system. So all this steel that we see here is helping to hold up the walls of the excavation. Again, this entire system would be engineered, so it would be designed by an engineer. Likely it would be you, the contractor, providing that design work. The owner would not typically provide that design. So here is the stair tower that I talked about before. So that's a scaffolding type system where it's erected, start on the bottom and they stack all together. So it's a staircase all the way up, and then you can get out here on the side. So the photo on the right here is what I talked about, having multiple machines doing the excavation. So you can see in this photo that there's there's 3 excavators, and then there's a dozer in the bottom. So the dozer is pushing all the excavated material, so pushing all that material over to the side. This excavator picks it up, throws it to where, well, doesn't throw it, but places it to where the next excavator can reach it. And then this excavator passes it to the upper one, where this one up here is loading the trucks and hauling the material off site. So you can see this would be a relatively expensive excavation. So you're still only doing, 20 cubic meters an hour, maybe less, but you have 4 machines here doing that volume. Maybe it's even less than that. Maybe it's 15 cubic meters an hour. So instead of 1 machine, you have 4. Maybe there's multiple dozers in the bottom as well. So again, it really depends on how big this excavation is. Okay, so shoring and anchoring. So used for vertical or near vertical slopes. So beyond what is structurally sound. So meaning if you were to dig ground at quite a steep angle, so almost vertical, it would not stand on its own. So that would mean it's not structurally sound. It would fall down. It would slough into the hole, which of course is dangerous. These types of systems are engineered. So again, a geotechnical and or a structural engineer would design these types of systems, the shotcrete shoring with the anchoring system. So these specific type of systems, so again, the shotcrete with the soil anchors, they're built at the same time with the excavation. So what I mean by that is you don't do all the shoring first and then excavate. You do a little bit of excavation, a little bit of shoring, a little bit of excavation, a little bit of shoring. So it's very slow, very costly, but it works well. Again, we'll get into an example here after the PowerPoint of what a system like that would look like as far as estimating. So typically consists of drilling in anchors, drilling the casing for the anchor, installing the anchors with grout, installing a steel mesh on the face of the excavation, shotcreting that face. So again, that's the blowing of the concrete onto the face. Any additional bracing is required for any adjacent property. So we won't get into that last bullet with our example. We'll look at these three here. So again, with those three bullets, you're also excavating in between. So you would do what's called a panel of excavation. You would then drill in your casing, put your anchor in, grout it, put your mesh screen on, and then shotcrete that face. So then you would go to the next one and do the next piece. So it sounds slow and time consuming, and it is. So here's a photo of that. So here on the left is a photo of the drilling. So this machine runs off of air pressure, so that's what the hose is. There's a large air compressor over here that operates this machine. So right now, this machine is drilling in likely the casing. Can we see the anchor? Yeah, it's either installing the anchor or it's drilling the casing. So you can see some of these other panels the mesh has been put up and the shotcrete has been sprayed. Yeah, this isn't the best photo. I'll do a sketch here of exactly what I mean by excavation, then shotcrete, excavate, then shotcrete. So this is what a typical anchor assembly looks like. So here's your shotcrete face. So the anchor goes in on an angle. So your engineer would design what that angle is. So it's not horizontal, it's at some angle down. So you've got so there's a casing, which is this diameter here. Inside that goes an anchor rod, or tendon as shown here. And then the void between the casing and the anchor is grouted. So we'll be calculating that grout volume. And you're told the length, so the bonded length, meaning the length of anchor that needs to be grouted. That's what bonded means. So unbonded is this initial section here doesn't have grout in it. So the anchor goes in. So then the mesh screen is applied here. Then the shotcrete is sprayed. So that concrete, that sprayed concrete, then has a certain amount of time to cure and to harden. So then After that has hardened, then this assembly here, this red assembly, so there's a plate, there's an anchor head, there's a jack. So tension is applied to the anchor. So the anchor is not moving. This jack is pulling very hard on the anchor. So what it's doing is it's pulling this plate into the shotcrete. So it's holding the shotcrete face there. Again, I'm not going to get into the engineering aspect of how this works. You just need to know the basics of how these go in. So this person here on the left is spraying the shotcrete. It's very messy, very dirty. You're literally spraying concrete at high pressure onto a wall. Not all of it sticks. Some of it flies all over the place. So if you're an estimator on a job site where shotcrete is happening, I highly recommend going to watch, but don't get too close. This person here, you can see he or she is decked out in all of this gear. Every piece of skin is covered with protective equipment, gloves, face mask, etc. So you can see the mesh there underneath. Here's a shotcrete that's already been sprayed. So this person is filling in this section here of shotcrete. These are previously installed anchors there and then along here. So the photo on the right, again, additional bracing. So looks like this is a different type of system. So this looks like H piles. So think of the letter H. Where'd my mouse go? There it is. So here's an H pile right here. So, or an I-beam, some people call it. So it looks literally like the letter H or I with some height to it. So these are pounded into the ground. So vertically at some spacing. So in between each one, timber lagging is slid down the slot in the H. So that's what this shoring system is a timber lagging H pile type system. They've also got the Wailers, again, steel beams that run around all four sides. You can see one here. And then they've also got additional corner bracing. Again, all of this to help support the initial shoring system that's been installed. And once again, your engineer would design that. So pile driving. So different types of piles. So compression meaning being squeezed together, or tension being pulled apart. Piles can be various types of materials. So steel, timber, concrete are the three main ones. Steel being probably the main type, timber and then concrete. The type of existing soil conditions impact the productivity of installing piles. So if the ground is more dense, it takes more effort to install the piles, those types of things. So equipment impacts the productivity. So depending on the equipment that you have, different types of hammers. So diesel, like drop hammers, hydraulic, vibratory hammers, different kinds of pile driving type equipment that are hung from a crane. Depending on the length of the piles, you may need to splice individual piles together. So you pound in the first section. Once the top of it gets near the ground surface, then you can grab the next section, stack it on top. If it's steel, it's welded together, and then you can continue driving. So size of the work area. So depending on what the spacing is of your piles, you could have more or less depending on the tightness of the grid. So here, photo on the left, here is a crane. So it is installing, looks like pipe piles, so steel pipe piles. So the grid, so the pattern is provided to you, the estimator. So for this one, because this is a permanent installation, these piles are permanent. The design engineer for the project would design these piles. Whereas on the previous slides where we looked at sheet piles and the H pile system, that's all temporary shoring. So that comes out of the ground once it's no longer needed. So if it's temporary, the contractor has to design it. If it's permanent, then the project designer, the design consultant would design it. So this crane is installing pipe piles. Looks like with a drop hammer or a diesel possibly. So really heavy weight is dropped and it pounds the pile into the ground, is basically the thought process for drop type hammers or the diesel type. So this other photo here on the right, so vibro sheet pile with pre-augering. So there's an excavator here. It has a special attachment on it with a vibro head, so it shakes. So it can pick up the sheet, get it vertical, place it on the ground where it wants to put the sheet, and then the operator in the cab here can push a button. This whole assembly vibrates, and then the boom and the stick of the excavator push the sheet into the ground. So that's the vibro sheet pile. This pre-augering, so that's what this machine is doing. The ground is so hard that this machine cannot pound the sheet into the ground. So the auger drills holes all the way along to loosen up the ground so that this excavator can pound these sheets into the ground. So jet groating, another type of system. So injects grout into soil under high pressure, creating a soil cement column. It consumes, so this type of method consumes a large quantity of cement. It requires space on the job site for a batch plant, so you're mixing your concrete on site. This should probably say concrete, not cement. It says produces significant cementitious waste that is costly to dispose of. So as the high pressure is blowing this soil cement into the ground, that same type of mixture is also shooting out of the ground. So again, it's a very messy type of system. Not the most environmentally friendly type system. So doing it near a waterway is could be quite expensive with all the environmental controls that you would need. So you need to manage the waste. So you couldn't let any of this cementitious material get into any waterways. So here is the system. So schematic type thing. This is the actual work of it happening. So a hole is drilled. So the probe goes down and it spins around and it's shooting out the grout material into a column. So the probe is pulled all the way up so that a column fills this entire section here. So then the machine does multiple columns that touch each other. So they're all in contact with the next one. So it's a continuous wall of jet grout columns. So this would basically be impervious to water. So as long as all the columns are in contact with each other, theoretically water would not come through it. So that could help with your dewatering. You would likely still need dewatering as the water on the bottom would come up. So you would need to dewater the bottom section if you're into the water table. So it looks like there's two machines here doing this work. So there's support equipment, there's compressors, generators, quite fairly specialized. Again, that Hayward Baker company, they do this type of work. So checking out their website, you can learn more about jet grouting. So next one here, stone columns. So this is, it's kind of similar to jet grouting, but instead of using soil cement mixture, you're using rock only. So as it says there, technique for soil stabilization that introduces aggregate into the soil. It densifies it. So again, this stone column method will increase the density of the ground. So again, if you have a heavy structure to be built and the ground isn't dense enough to support that heavy structure, this is one option to densify the ground. So you would need to import aggregate. Again, there's specialized companies that do this. There's a few of them around town that have the capability to do this type of work. So again, it's a specific pattern. For stone columns, all the columns don't touch each other. They are spread apart, usually approximately 2 meters, maybe a little more on center. A stone column would be anywhere from 0.7 to 0.9 meters in diameter, somewhere in that range. So there is space in between each column. So here is the rigs doing it. So there's a crane just off the photo here, another one over here. So there's a probe. That's what this pipe is. This hopper here goes up and down. So this one is down at the moment. So there should be a loader. Can we see it? No, there's no loader there. So this probe gets vibrated into the ground. So down as deep as required. So then as it's vibrated, this hopper full of the stone gets filled up with a loader and then gets pulled up using the crane, and it tips into the hopper at the top here, and all the aggregate comes down the probe, gets to the bottom of the probe, and the probe is inserted and pulled out repetitively. So what it's basically doing is it's pushing the stone into the ground, creating those 3/4 of a meter diameter stone columns. Again, it's pushing the existing ground away from the new stone, so which in turn densifies the soil. So stone columns have two different types of methods. This is the bottom feed. This would be the top feed method. So the wet top feed. this would be considered the dry bottom feed. Bottom feed meaning the stone is introduced into the column at the bottom of the column, so way down in the ground here. Versus the wet method, the loader simply grabs a loader bucket worth of gravel and dumps it right here. So the crane lifts and lowers this column here, pounding that stone into the ground. All the while blowing water into the hole to help blow the stone down. So that's where the water comes from in this wet top feed method. Of course, this one is more environmentally unfriendly. You can see all the muck here. So again, if you were adjacent to a waterway, this would be tougher to contain all the spoil. This method here, the dry bottom feed, is more environmentally friendly. There's no water introduced into the columns with this method. Again, both of these are both stone columns. They both densify the ground, just two different methods of doing it. Soil mixing, that's next. So it's exactly what it sounds. It's mixing soil with additives. So whether it's cement grout mixture, or maybe you're mixing with clay, or maybe it's a mixture of both with the native material, the native ground. So it can be used to stabilize the soil, construct cutoff walls. So again, a cutoff wall is to prevent groundwater seepage. So with this method, significant slurry waste is common. And again, it's difficult to handle. So again, it's an environmental concern that you would have. Consumes a significant amount of either the cement powder or clay, depending on the system that you're mixing. This type of system was actually used at the City of Burnaby Works Yard. The ground there was too soft to build the structures on, so a specialized contractor came in and did this soil mixing, soil stabilization treatment over the whole area before the building contractor came in. So soil mixing, so we have a drill rig to get down to the depths that you need to get to. Special attachments for mixing the materials, batching up the materials. Again, there's specialized companies that do this as well. Again, it increases the density of the ground, or it can, I guess, if you're using cement mixture, that'll increase the density. If you're using a clay mixture, that would be intended to cut off water. Because these are permanent methods, this type of system would be designed by the designer. The contractor would not have to design this. So the next method, so Caisson drilling, so used when existing soil is being fully displaced. So you're basically drilling a hole in the ground to a certain depth, certain diameter. You're backfilling this hole with different types of material. Sometimes it's aggregate, sometimes it's concrete, sometimes it's reinforced concrete, sometimes structural steel. Can be used when below ground obstructions are concerned. So a couple photos here. So a hole was drilled, right, to whatever depth. based on whatever diameter was designed. So the rebar cage is lowered in. This bar here holds it in place so it doesn't drop any lower. As well, oops, keeps it centered in the hole so it doesn't flop over to one side. Then this hole would be filled with concrete. So here's the drill rig. These are the drill bits. Steel pipe. So there's an auger here. So sometimes the casing is left in the ground, other times it's not. It all depends on the design. And yeah, so sometimes there's a casing that's left in there, so the steel casing might be left in the ground if there's a concern that the hole is going to collapse in on itself. If it'll stand without a casing, then of course it's cheaper. You don't need to buy the steel pipe to put in the ground. Yeah, it could help with keeping water out. That's true, yes. So adding a casing or a steel pipe could help prevent or reduce the amount of water. You'd still have a little bit of water coming in from the very bottom, but theoretically you would have none coming in from the sides. So alternative techniques require significant ancillary equipment and materials. So any other questions on the PowerPoint? We're going to have a break first, it's 8 o'clock. After the break, we'll do an example. I'll go through it, show you kind of how it works, of the Shotcrete excavation soil anchor type system. That's what this week's exercise is also based on. So you'll have kind of a template of how to work through the problem. So it's 8 o'clock now, or 8:01 according to my computer. So let's come back in 10 minutes and we'll do the example. I'm going to pause the recording just for the break. Okay, so we're back. Before we get into the example of the Shotcrete soil anchor, I forgot we needed to relatively quickly go over the soils reports. I've mentioned soils reports a few times throughout this course. I will not go through them in great detail. That could be its own class to itself. But I do want to mention some of the important parts of soils reports. So one of the handouts that I provided for this week's class was the soils report handout, which looks like this. So again, we're not going to read through every sentence on here. I will highlight some important things. I would hope that you would go through and read this entire thing. It'll give you a kind of a summary of what a soils report does, how it can help you as the estimator, what the purpose of the soils report is. Its intended purpose isn't initially for the estimator. It's for the designers. So we'll spend a few minutes on the soils report, and then we'll go ahead and do the example of the Shotcrete soil anchors. So soils report. So they're prepared to provide the design engineer and the contractor with information regarding soil conditions at a specific location. So typically the design engineers produce all of this information so that the other designers can complete their designs. So structural engineers will use the soils report, things like that. So these reports are a wealth of information for the person that can properly interpret the information that's presented. Looks like I missed a period there. So the contractor wants to know what the subsurface conditions are so that they can produce an accurate estimate. So subsurface conditions. So the soils report tells you what's going on under the ground. So things that you can't see if you were to do a site visit during the tendering process. So some important things to look for. This is not an exhaustive list. Maybe there's other things that you're looking for. These are just some of them. So for instance, what elevation is the groundwater at? Whoops. Is there rock in the ground? Another one here, can the native excavated material be used for backfill? So the soils report will tell you that. If you have to dispose of all excavated material, or can you keep some of it to replace, put back into the excavation? Another important one here, how steep can the temporary excavation slopes be cut or excavated at? So this is where the 1-to-1 or the 3/4 to 1, maybe it's shallower, maybe it's 1.5 to 1. This is where you should first look for your slopes. If the soils report does not tell you an acceptable temporary excavation slope, then you fall back to what WCB says. So things like sometimes you'll be told if temporary shoring will be required, not always though. Sometimes you'll be told what the most effective shoring method will be, but again, not always. So geotechnical reports, they're basically set up all the same. They have kind of the same sections. So they all have an introduction, project description. So the field exploration and testing, site conditions. So what the people that were out on site doing their testing, what they actually observed, what the site conditions were at that specific day. This is kind of one of the most important sections. So the recommendation section. So the various explorations and tests, etc., are translated or dumbed down, if you want to read it that way. So they're translated into specific criteria, settlements, dewatering requirements, etc., to make it easier for all parties to read. Sometimes soils reports can be quite tough to understand. So it takes some practice reading through them and knowing what they mean. So maps, so soil logs, this is also another important section. So typically what happens is a soil exploration company will go to the job site. So they will be directed by a geotechnical engineer. So the engineer will tell them where to drill cores. So those cores are columns of dirt that are pulled out of the ground. So the dirt in those columns is analyzed. So the results of that analysis are summarized and produced into individual logs. So each core hole will have its own log, and we'll see an example of one of those shortly. So these logs, again, they contain a significant amount of information. Of course, it would only apply to that specific log. How far those details extend outside of that individual core hole, nobody knows specifically. And the soils engineer makes no guarantees of all of the ground being represented by the logs that they've done. So they do different things in the logs, tell you how dense the ground is by this blow count. If groundwater is encountered in the borehole, you'll be told what elevation it was at. You're told the moisture content of the soil, so how wet it is it dry, is it really wet? The classification of the soil, so this is where you're told if it's silt, if it's sand, if there's a bedrock layer, things like that. So test results, if from these logs, if any of the material out of the cores was, maybe a sieve was done on them, so you can be provided with a gradation of the material that's down deep. Basic clues. Must be understood. So these types of clues are provided to you in the logs. So again, we'll have a look at an example log and I'll point out some of those items. So some things like in the recommendations here, if the report is concerned with settlement, so that means the ground is settling, so it's sinking, or liquefaction, that's another geotechnical term. It could possibly suggest that the ground isn't very good, weak, clayey soils, maybe mean you need to over excavate. Soil bore logs. We'll look at a log. Yeah, all of this will be in the logs. So this one here, soil properties. Usually soils are described as loose, dense, hard, stiff, soft, that type of thing, etc. So of course, loose or soft ground means the ground cannot support a slope as steep as 1-to-1, so a flatter slope would be required. If you have a borehole that says, you know, there's a layer that's hard or that it's stiff, that may concern a pile driving contractor. Then they would see that and they would realize that they need to allow for bigger, more powerful equipment to drive the piles in, if there are piles on the project. Blow counts. So a blow count, this is just a definition of what that is. So it's a very important measure of soil properties. So it's a standard penetration test where a specific weight, so this specific weight, is dropped. The number of times that it takes to advance 1 foot is counted. So of course, the more number of blows that it takes to go 300 millimeters into the soil means the denser that ground is. So loose or soft soil would be blow counts of, say, less than 10, 10 to 50, fairly easily excavated. Blow counts of over 50, but less than 100. So it's likely going to be difficult to excavate. You may need to rip the ground. So the ripper is that big tooth that's on the back of an the back of a dozer. So as you approach 100 for a blow count, the ground is getting quite hard. And it's possible that you cannot dig it with an excavator. So exceeding 100, ground may be very difficult to excavate and possibly require blasting or some other type of ripping or type method in order to remove the material. Soil moisture. So optimum compaction moisture is usually somewhere around here, 8 to 15% is optimum moisture content. So if your soil is within this range, it's easier to compact, and you can compact it to a higher degree. Whenever you're below that or above that, it's tougher to compact, and you will likely not be able to compact it to the required density. So moisture. So the sieve analysis tells you the individual grain sizes of the soil. Atterberg limits, skip over that. So sometimes a compaction test is done. So we've talked about shrinking. So 5 to 15% is usually a typical shrink factor. So high clay content can shrink 25%. So blasted or ripped rock will swell as much as 25%. Permeability, so that's how quickly groundwater will travel through the soil, how permeable the soil is. So clean sands and gravels can transmit huge volumes of water and require massive pumping. Clay is relatively impermeable and releases water slowly. So each soils report that you read is going to contain a great deal of information. They're typically dozens of pages long. So there's no one thing, one test or one observation that will tell you everything that you need to know. So each test or observation is a clue. So by reading everything, you get the full picture of what's going on below ground. So this is something I should also mention. Geotechnical reports also include disclaimers and warnings that the ground conditions may vary from those found in the boreholes and the test pits. So geotechnical work is still as much an art as it is a science. So nobody's able to see exactly what's going on underneath the ground. By doing these boreholes, you can see at specific spots what's there. So as you read more of these things, you'll become more of an expert on them. So it's up to you as the contractor to decide what methods and costs you're going to include in your bid for any earthworks or embankment work. So this one here, I don't want to scare you, but if contractor makes a judgment error in their estimate, nobody's going to pay you for your additional costs. So this is a standard symbols page that's in every soils report. So borehole logs use these types of symbols. So gravel is always shown this way. Sand is always shown that way, etc. Silt, clay. So here's your description of your materials. So sometimes things are called very loose, sometimes they're called loose, compact, dense, very dense. So there's bullets here, or sub notes 5 and 6. So those would be your blow counts. So this section here is, again, it's just as important as anything else. So when the types of material are being categorized, quite often it won't say gravel, it'll say gravelly or trace gravel or something like that. So whenever you see these types of suffixes or these types of words included with the description of the materials, these are the percentages that are associated with that. So a trace means 0 to 10%. So a trace of sand would mean there's 0 to 10% sand. Or some clay would be 10 to 20% clay. So that type of thing. So all these particle sizes, so these are all your sieve sizes. So boulders are considered anything 200 millimeters and bigger. Cobbles 75 to 200 millimeters. Gravel is anywhere from 5 millimeters up to 75. Sand is this range here. And then the fines, which are the silts and the clays, are anything smaller than 0.075 millimeters. So you can see how silt and clay are very fine particles, which is why they don't let very much water pass through them. Okay, so this would be a typical borehole log. So up at the top, so you've got the test hole number. So typically there's a map of the job site, and all these test hole numbers are plotted on that map, so you can see where each test hole was performed. So it tells you here to see the drawing. Gives you the approximate elevation of the ground surface, so the top of the ground. Elevation 4 meters, approximately. So who did the drilling? So then the first kind of thing that you see here is the depth below ground. So they drilled 1, 2, 3, 4, 8, 9. Looks like they stopped about 9 meters deep, or just over 9 meters. This squiggly line here is your blow count. So that relates to this. So 0 is right here. Maybe I'll zoom in a little more. So 0 is this vertical line. So 10, 20, all the way up to 100. So you can see there's a blow count of 20, then it jumps up to 40. So it drops down to about 10 here, up to 20. So you can tell by how this blow count goes that it's initially, getting to be more dense, and then it just drops right off. So here it's very soft, all the way down, till we get back up to maybe 7 or 8 meters deep, and then it becomes more dense. So that corresponds to, if we look at this side of the page, so this is the soils description over here. So we just said this blow count was very low. It's quite a bit less than 10. So the description of the soil here is soft, and it's peat. So very low blow count. The material description is soft, so it's not very dense. Up here where we had the higher blow count of 30s and 40s, So we have compact sand. Oops. So typically the word that's all capitalized, that's the highest content of the material in that section. So for this section here, for this approximately 3 meters, it's mostly sand with some silt and gravel and a trace of organics. So organics could be anything from topsoil to wood chips, stuff like that. So there you go, partially decomposed wood fragments. So there's your soft, mostly peat. It's moist. So we get some, so there's your compact sand. So the blow count is increasing. So the ground is getting more dense, it's compact. So these are your symbols. Again, we looked at that on the previous page. This here, that upside down triangle with the 2 lines, that's the approximate groundwater elevation, or the groundwater location, I guess I should say. So because this is depth, it's approximately 1.2 meters below the surface. So this column here is depth. This one over here is elevation. So because we started at 4 meters, 1 meter down would give an elevation of 3 meters. 2 meters down from elevation 4 is elevation 2, which is 2 meters deep. When it was done, so who it was done by. So Thurber is the geotechnical engineer on this project. So down near the bottom, end of hole. So you're sometimes told why the hole was ended here. So it stopped at the required depth, so they didn't want to go any deeper. Sometimes it'll say at refusal. So the coring bit hit something, and it physically could not go through it. So sometimes you'll be told that it hit an obstruction. So water is observed 1.2 meter depth. So this is a typical borehole log. So on any particular project, you could have maybe 5 or 10 or 15 or more boreholes. So you want to look at these and get a general idea of what the ground looks like. Maybe some parts of the project have deeper excavations than others. So for those deeper excavations, you want to look at the corresponding borehole that applies to that deeper excavation and see what's down there. The last thing I'll mention before we get into our example problem is these little circles here. And there's 2 more here with numbers next to them. So those circles here, these ones in this grid, they relate to this numbering system as well. That's your water content. So looking at this first one here, if we look straight up, so if I drag my mouse straight up, it's somewhere about 35 to 40% moisture content. This one here is probably about 30. This one's similar. So these 2 here, our grid only goes up to 100. Well, these 2 are over 300%. That's typically what you get in peat. It's holding so much water, this peat, that the water content is just, it's sky high. It's soaking wet, that peat. Up here above the water table, right? So the water table's right here, we're at about 10%. So this is drier up above the water table. So this same grid is used for the water content as well as the penetration, the blow count. Any questions on the soils report kind of summary that we went through? Okay, so the last thing we'll go over is we will do the sample problem of the soil anchors with the Shotcrete, which again is, like I say, you as a question, rectangles that are half black and half white. So if I get back on my screen, these right here, is that what you're referring to? Yes. Okay, so that symbol you can see matches this symbol right here. Whoops. You need to highlight everything. So that's the whether the sample was disturbed or not. So as it came out of the core bit, did it come out as one piece, or was it did it come out you know, fragmented or not as a cylinder? So these were all disturbed. We're told by that symbol. Yeah. So the whole 9-meter column came out as bits and pieces. So if a core was done into, say, where the majority of the material was like a clay or a silt type material, that would typically be undisturbed. So when the core bit was pulled out of the ground, a cylinder of clay would come out. So it wouldn't break into pieces. Is what that means. Okay, so let me close this down. Sure, no problem. So let me move this. Okay, so this here is so it's a profile. So we're looking at, consider that we're standing here looking at the wall. So this isn't a plan view, this is a profile. This section over here, so I've drawn a section through here, A, so we're looking that way. So this is that section. So up here is the ground surface. So maybe I'll put that on here. So top, ground surface. That's before you started excavating. That's what that surface is up there. Down here would be maybe the bottom of your excavation. So bottom excavation. So what our example question is we're told we have a 30-meter long wall and the depth of the excavation is 5 meters. So we want to be able to, if we look at this section here, we want to be able to cut vertically here so that all of this will come out. So we'll have a vertical excavated face right there. Okay, so in order to do that, we have to construct this soil anchor wall. So in the details of our question, we're told that the first row of anchors will start 2 meters down from the top, and the anchors will be on 2 meter spacing. So that's what we have here. So they're 2 meters this way as well as 2 meters that way. So the first anchor comes in from the edge by half of that spacing. So if we have 2 meter spacing, the first anchor is a meter in from the start of the excavation phase. So we got a meter in, and then 2 meters, 2 meters, 2 meters, all the way down. So the way this would work is, I mentioned previously, let me erase this here, that soil anchor, shotcrete walls, and excavation are done at the same time. You don't do all the shoring first and then come in and do all the excavation. It's done in stages. So what do I mean by that is, we're going to look at both this profile and this section here as we go through. So if you were to start this excavation, you could do the bulk excavation. So all of this material here, you could dig out, right? This could be your temporary cut slope here. So all of that could be dug out. So you've left this wedge, and I haven't dimensioned it because it doesn't really matter what it is. Maybe it's 1-to-1, maybe it's steeper than that, maybe it's 3/4 to 1. So you've left this wedge of material in there. So the way the phased excavation works is, after you've done that bulk excavation, you need to come in and do pockets of excavation for the anchors. So how does that look? Let me draw it with colors here so that it shows up well. So you would come in and excavate something like this. So if we showed that here, you'd come down approximately halfway between your 2 rows. So that would be your depth down. And then you would go halfway between each anchor on either side, where the design anchor is supposed to be. Now remember, we haven't put any anchors in yet. We're only excavating first. So you could excavate a slot here, then you would skip a slot. So we're going to skip, I'll just do it dashed. We would skip this slot. So that bit of dirt is left there, that's inside the purple dashed lines. So then we would come in and excavate again the next slot. And then similarly, we would skip the next one. So you would do this all the way along until you've excavated out every second anchor location on the top row. So I won't draw all these in, but you get the idea. So this is excavated, and yeah, maybe just I'll leave it as the green is excavated, purple is not. So I'll shade this in here maybe. So we've excavated that out every second slot. So then what comes next is the shoring crew comes in, drills in the casing, puts the anchor in, and groats that anchor in. Then you come along and shoot the shotcrete facing. Use a different color for that. On the face here. So anything that you've excavated, you can put your steel mesh on. So that would be the reinforcing for the concrete. And then you would spray the shotcrete onto the blue face there. So now, remember, we can't go all the way to the bottom because we haven't excavated down there yet. So you would do that anchor and then the mesh and the shotcrete. So that procedure you would do at each one of these green excavated slots. Sorry? Was there a question there, or was that an accident? I'll assume an accident. Okay. So yeah, at some point you will have excavated every second one on the top row. You will have put all the anchors in, or sorry, every second anchor in on the top row, right, at all the green slots that you've excavated. You will then have done your mesh and your shotcrete at all those green slots. So at that point, you could come along and excavate the slots that you skipped. So you would do that purple one, the purple one, the purple one, etc., all the way down, and do that same procedure with every skipped slot. So again, drill the casing for the anchor, put the anchor in, grout the anchor in, put your mesh reinforcing on the face, and then shoot your shotcrete on it. So that would be your procedure for the top row, and then you would do a similar type procedure for the bottom. So after you've got all the anchors in on the top row, you would come down and do the bottom row as well. I'm going to erase this person here. With the same skipping of every second slot, just like we did on the first row. Now, the reason I tell you this is to illustrate how slowly this procedure goes. This slot, this first green slot that we excavated, is 3 meters deep and it's 2 meters wide. So it's 3 meters deep and 2 meters wide. So depending on how much of a wedge we left here, maybe you're excavating 10 cubic meters over there. Maybe it's 15. So it's slow work. You excavate 15 cubic meters here, then you do that here and here, and then your excavation crew stops and it waits while the shotcrete crew comes in, does the anchors, does the shotcrete facing. So again, I'm trying to drive home how slow this shoring method is, but it gives you that vertical face that the deep excavation people like. For example, the deep holes in downtown Vancouver where the new high-rise is being built. These types of shoring systems can be installed on quite very deep excavations. So, 10, 15 meters deep, possibly deeper depending on the ground and the spacing of your anchors, right? The length of your anchors, that type of thing. Any questions so far on what I've shown here? No? Okay. So I'll show the rest of the page. So down here, this is a blow up of an individual anchor. So this is looking at, so if the anchor is sticking into the soil face like this. So on the outside of it is the barrel, or the casing as it's called. So for our example, we've got a 50 millimeter diameter barrel and a 32 millimeter diameter anchor. Obviously, there's some space around the anchor. That's the space that gets corroded. So you're using your area of circle calculation. So you first calculate the volume of the barrel, so the volume of the 50 millimeter diameter barrel, and then you subtract from it the volume of the anchor. That'll give you your grout volume for one anchor. Then you simply multiply by the number of anchors that you have. What else could I say? So why don't I do calculation for the amount of grout in one anchor. So we're told in the question that we have a 3 meter long grouted anchor. So we're told that in our example question. So whatever areas we calculate here, we'll be multiplying by 3 meters long to get a volume. Okay, so let's calculate the volume of the barrel. Actually, the way I like to do it is calculate the area of the barrel. So area of the barrel, and then subtract the area of the anchor, and you multiply that by the length of the anchor. Anchor length. Okay, so area of the barrel. So area of the circle, a couple different ways to calculate it. I like to go with the pi d squared over 4. You can also do pi r squared. Either way will give you the same answer. So the barrel we're told is 50 millimeters. So start with pi. So diameter of the barrel, I will use meters. Meters, so 50 millimeters is 0.05 meters. So we'll square that, divide by 4. So running that through our calculator gives me 0.002 square meters. So that's the barrel. So do the same thing with the anchor. So area of A, so A is anchor. So pi 0.0, so 32 millimeter diameter anchor. So 32 millimeters is 0.032 meters. Square that, divide by 4. That gives you an even smaller number of 0.0008 square meters. So subtract one from the other. So 0.002 minus 0.0008 is 0.002 is 0.0012. So that's the area of the shaded green that we will fill with grout. So then we need to multiply it by 3 meters to get the volume of that grout. So times 3 meters is 0.0036 cubic meters. So pretty small volume. Now I've got a little conversion here for this example. So 1 cubic meter is 35.3 cubic feet. The reason we're converting into cubic feet is our bags of grout. 1 bag is 0.7 cubic feet of grout. So we want to convert from cubic meters into cubic feet in order to determine how many bags of grout. Okay, so first thing we do is take this. So that's our cubic meters. So I'll just write it over here. 0.0036 times 35.3 cubic feet per cubic meter. So that'll give us the number of cubic feet. So 0.0036 times 35.3. So 0.13 cubic feet. So 1 anchor needs 0.13 cubic feet of grout. So how many bags is that? So 1 bag is 0.7. So we simply go the cubic feet divided by 0.7 cubic feet per bag will give us the number of bags. So 0.13 divided by 0.7. So we need 0.19 bags. So 0.19 bags per anchor. So to find your total number of bags, you simply multiply bags per anchor times the number of anchors that you have. So up here, we've got 15 anchors per row. So 15 there and 15 there. So that's 30 anchors total. So we would go 0.19 times 30, which is 5.7. So we would need 6 bags of grout. I can scan this and upload this for your reference for doing the exercise. Other things like, let me grab a pad of paper here. So in this example, we need to calculate other things like how many square meters of the reinforcing mesh do we need? Well, how do we calculate that? It's simply the wall area. So 30 meters times 5 meters. So we need 150 square meters of mesh. We determined the number of anchors. So we had a 30-meter long wall. We're told the anchor spacing is 2 meters. So 30 divided by 2 is 15. So 15 anchors per row. Now we know the height of the wall is 5 meters. So we know that 2 rows of anchors will fit in that 5 meters. So it would be 15 times 2. So 15 anchors times 2 rows. So 30 anchors. So the only other thing I'll mention here is let's say, so the shotcrete. So what's our area of shotcrete? Well, the area of, so that's the shotcrete wall, that vertical face. The area is simply the 30 by 5. It's the same as the mesh. So the area of shotcrete is same as the mesh, so 30 times 5 meters, 150 square meters. So what's the cubic meters of shotcrete that we need? So let's say that the thickness of the shotcrete is, let's say it's 150 millimeters. Just for our example. So how do we calculate the cubic meters of shotcrete? We take our area, multiply by the thickness, right? So 150 square meters times 0.15 meters, 150.15. So that's 22.5 cubic meters of shotcrete. Okay, so one last one. How many meters of anchor rod do we need? We said we had 3 meters of grouted anchor. We're not told anything in addition to that, so we have to assume that each anchor is 3 meters long. So how many anchors do we have? We said we had 30 anchors, so 30 anchors times 3 meters long is 90 meters of anchor. Okay, so those are the types of calculations that you will need to do on your next assignment. So I'll scan both of these pages and upload them. I will also upload the soil anchor assignment or exercise to Learning Hub. So does anybody have any questions on those calculations? Okay, so give me just a minute or two to scan both of these pages, and I will get all 3 of these uploaded to Learning Hub. I'll be back in just a moment.